rigid surface. So once again, to just make you recollect what we have learned, is that if the wave gets reflected from this rigid point, it would get inverted. When it comes back, it would get inverted like this, right? The wave pulse gets inverted. Now we are going to see this idea in a little bit of detail, right? So what exactly happens over there when the wave arrives and all that? Let's start. So I am going to explain this with a series of diagrams. Okay, my voice is clear? Alright. Okay, so using a series of diagrams, let's see. First of all, this is the case where we are going to draw where the wave pulse just touches. Okay, like this, it just touches the wall. At that time, the inverted wave pulse, you can imagine again, remember, I am saying you can imagine that the inverted wave pulse is over here, okay, and it's going to travel towards the left side. This is going to travel towards left side, this is going to travel towards right side. So you see here, at this point we have two waves. Remember, this is imaginary, this is my way of explaining it, and it's perfect way, to be very frank. It's that this one is going towards right side, this one is coming towards left side, but both the waves here give displacement 0. So that's why the total displacement of this point will be 0. After some time, this will move a little bit towards the right side. So let's draw another case where, again here is the wall, but a little bit of the wave pulse has been over here, right? Okay, so what does that mean? It has moved forward by this distance. Did you understand what I said? Comparing diagram 1 with diagram 2, you can think of as if it has moved forward by this much distance. Okay, so that's what I have drawn. So this is wave which is incident, right? This is the incident wave. But what will happen is, this part of the wave pulse will already be reflected. I repeat, this part of the wave pulse will already be reflected and it would become inverted. So if this is mean position of the string, right, if this is mean position of the string, you would get an inverted wave pulse starting from here. Did you understand this part? What's this actually? What's this? You can also think that the imaginary reflected wave that we were talking about has come forward. Do you realize what I am saying? This imaginary reflected wave has come little bit towards the left side. So now it's like this. Did you understand? Right? So ultimately what will happen, it's just that here you just have a reflected portion, right? So this part is real and this is not there, this is just imaginary. So basically if this is plus 1 mm, then this will be minus 1 mm, y downward. So ultimately the net displacement will be 0. Okay, ultimately the total displacement here is going to be 0. Again, it's the idea that whatever part has hit the wall, that will get reflected and inverted, right? So basically what is happening is that the last point, the end point, always has two opposite displacements, right? Here it was not a concern because both were 0. Now it would be something like plus 1 and minus 1. Next diagram, the wave would move a little bit forward. So let's say it reaches a point like this, where the peak is supposed to come at the wall. This is again the incident wave that is still traveling towards the right side. Again, what's this? You can imagine that what if this one moves a little bit towards the right side? Wouldn't it become a shape like this? Okay, but at the same time this imaginary reflected wave will also come towards the left side. So over here, it's like half of the wave pulse has been cut and it has been put here. Did you understand? Yes or no? This is the reflected wave already starting to move towards the left side. Make sense or not? It's a whole lot of imagination, remember. Right? Again, where is the right hand half of incident wave? It's gone. It got reflected and it is now inverted. It's here. I hope you understand what I am saying. The right hand part of this, okay, this one is actually inverted and now it's going back, so it's here. So what is happening is, again, that if here the peak is at 2 mm, then this will be at 2 mm once again. So because of that, y will be something like +2 and -2, so that is 0. Again, using superposition principle, that here at this point of the wall, there are two waves. There are two waves acting simultaneously. Which two waves are acting simultaneously? The incident wave that is going towards the right side and the reflected wave that is going towards the left side. Right? So upwards +2, downwards -2. It's exactly symmetrical here. Right? A little bit more time and this will move even a bit more forward and this will move a little bit leftward or left side. Okay, so then it would look like this. So now it has reached up till here. So what that means is most of the part has been reflected. But again, this pattern that has gone on that side will get reflected and it will appear here. I hope that makes sense. So now there are two waves once again. Right? This upper one is incident wave and this one is reflected wave that is going towards the opposite side. Right? So because of this, once again, it's quite clear. See, if you draw one shape, you draw one line, okay, and then you take this part and you reverse it and you draw it here. Then do you realize that whatever is the distance here from mean position, that will be the same distance from mean position, but in opposite direction? Yes or no? Do you realize that if this is 3 mm, then this will also be 3 mm? Yes or no? If you take this part and you cut it and put it inverted, right? So this is what is actually going on over there, right? So ultimately, at every point of time, it's going to be just like this. Okay, suppose 1 plus and -1. So finally, the last diagram of importance is that just like here, the incident wave was touching the wall. The last one will be where the reflected wave is just touching the wall like this, and now it's going towards the left side. Where is the incident wave? It's like it has completely passed through. Remember, now this is imaginary, right? Nothing was behind the wall. Remember, nothing is going behind the wall. We are talking about reflected wave. This wave is not there. It's just a way of drawing it, right? So basically what we have done is this pattern inverted and going towards left side. Understood? I repeat, this pattern inverted and going towards the left side, just like we have it in every diagram. Okay? So you can see in various stages what will happen to the fixed point here. It will not move because every time incident wave and reflected wave will exactly cancel each other. The numbers are random. Okay, don't say how did you get to. Like I said, numbers are only for example. Okay, they are not important in any manner, right? So this is what will happen at a fixed point. Okay, this is what will happen at a fixed point, right? I'm erasing all of it from the board. Okay. let's write a sentence related to the same thing, in slightly more physics terms. At a rigid or a fixed boundary point or end point, the reflected wave gets a phase change of pi. The reflected wave gets a phase change of pi. Okay. Pi means 180 degrees. What does this mean? See, it's that the pattern that was like this in the positive, after reflection it becomes inverted, right? So basically whatever y was positive before reflection, that y will become negative after reflection. Do you understand what I'm saying? Okay, and what this means is that mathematically the relation between such inversion would be very nicely explained by this kind of behavior. Have you? That if you have got some angle theta and if you write sine theta plus pi, then that will be minus sine theta. So what this is saying is that if you add the angle by pi, then the value itself becomes negative, right? So this was sine theta earlier. You add pi, it will become minus sine theta. Understood? So that's what this behavior is showing. You may also subtract pi. That's not a problem. That's why I've written change of pi. Add pi, okay, no problem. Subtract pi, then also no problem, right? In both the cases, the end result is the same. I repeat. In both the cases, the end result is same. So you can say, does the angle increase by pi or decrease by pi? No problem. You can do whichever you like. It gives the same result every time. Okay? Yeah. Now we have a question here. What happens when two sound waves come together? Yeah, same thing. Superposition principle. Even when two sound waves come at the same point. Even when two sound waves come at the same point, there is superposition. Is that okay? This idea is valid for all kinds of waves, not just on string, also for sound or even for light, to be very frank. Okay? It is true even for light. Okay? It's actually true for all kinds of waves. This idea, superposition principle. Well, I'm erasing this sentence. Hopefully you have understood what we have written here. Let's go to the next. Both are cancelled, yes, at that fixed point only. At any other point they are not cancelled. That's what you should understand. Right? There is a question that if this wave is inverted, then are both cancelled? Yes, they get cancelled because they are together at fixed point only. At any other point they are not cancelled. Obviously, think about it. Let's say you send one wave pulse, it goes like this. After the incident wave hits that, only then the reflected wave will come back. So the two waves are not at the same time at the same point. I hope that makes sense. Okay? Right? It's like, let's say your father is at your home, right? So when you will go home, only then your father will come out. Does that make sense? It's just like that. You are the incident wave and your father is the reflected wave. Clear? Both are not at the same point at same time on the road. You are only there together at your house. Okay? The fixed point. Well, now, what happens if that point is not fixed? For example, Okay, so let's write reflection from a loose end. Okay, or you could say movable end. Right? What if instead of being fixed with a nail, what if it was a loose end or movable end, free end? Basically, you can also write free. See, in reality, remember this, here also we are actually dealing with ideal cases. Because the truth is, however hard you may fix a nail on a wall, it can never be immovable or it can never be fixed. It will always move a little bit. Right? Similarly, something that you are calling loose or free or movable cannot be absolutely free to move. There will be some friction and all that. Right? So both of these cases are ideal cases, but they work really very well. Okay? So how to make or how to imagine this kind of behavior? Let's see. Suppose there is a rod. Let's say. Okay? Suppose there is a vertical rod which is fixed to the ground. And now you take a rope. Listen to this carefully. You take a rope or a string, and at the end of it there is a ring. And that ring has been put over this rod. Did you understand what I have drawn, everyone? Did you understand or not? Yes or no? Right? So now, think about this ring. Generally, if the friction is not that much, do you realize that this ring is free to go up and down? It's free to move in the vertical direction, yes or no? Assuming it's not very heavy also, otherwise gravity will play a big role, right? Let's say this is a comparatively light ring. Okay, I hope that makes sense to you. It's a light ring. Okay, this is a way of making a physical situation that goes by this idea. Okay, right? Let's see. So what happens? Okay, this is a light ring here and this is relatively free to move. What happens if you take this in your hand? So that becomes the source, and you give it a wave pulse. So as usual, let's say you move this up first and then you move it down. So you get a wave pulse like this, going over to that. Right? Okay. Now, what happens over here is, listen to this carefully. Let's say this wave pulse reaches all the way up to the ring. Let's say. Now, obviously, I'm sure you would have understood this, that the ring will go upwards, correct or not? Obviously, the ring will go upward. There is no doubt about that, right? But unlike the previous case here, what is happening is that this is not fixed. So when this wave pulse arrives here, when this wave pulse arrives at the ring, it will not get opposite force. If you recall what I told you about in the fixed case, right? The wall will apply opposite force. But here there is no such thing because this is free to move. So that's why this point, that is the ring itself, which you can think of to be the last point of the string. Okay, so this will go up and it will go down as expected. Right? You understand what I am saying? This will move up and then it will move, or it is supposed to move down. But the moment this starts to move, it is going to be that the energy that has traveled up to the ring, okay, going from your hand, energy traveled along with the wave up to the ring. Now that energy will be sent back by the ring. I repeat, that energy will be sent back by the ring. In which way? Well, it's that if this goes up and down, this is going to behave like a new source. I repeat, if this string moves up, moves down, the ring moves up and then down, then the ring is going to behave like a new source. So what it will do is, you think about it as follows. Let's say here is that ring, okay, and here it is attached to a string, right? Just put this out of your mind for a while, okay? Just put this out of your mind. Focus here. Suppose you were to take this in your hand or by any other means, and you will move this up and then you will move this down. What do you think will happen to the string? I repeat what I have said. If you take this ring in your hand and move this up and down, what will happen to the string? Yes, a wave is generated, isn't it? A wave is generated. String will not move up and down. There will be a wave on the string. Right? So, basically what I am trying to get you clear with is that when the ring moves up and down, it's going to create a wave like this on the string. Yes or no? This is clear? This is clear or not clear? Okay. Right. So, what is basically happening is, now we come to this picture. What is basically happening is that as soon as this wave arrives at the ring, it's going to make the ring start moving. Now the moment ring moves, it's going to generate another wave. Did you understand? I repeat what I said. This wave comes here, the ring will start to move up, correct? Now the moment the ring moves up, there will be another wave generated, a second wave generated on the string. Yes or no? Clear or not clear? Okay. But the first wave was traveling towards the right side. Okay, but the second wave that is generated will be traveling towards the left side. So this is basically the reflected wave. Why is this not inverted? Simple reason. Because if this is the source, first the source moves up, then the source moves down. So you know that whenever you take a string in your hand, and you jerk it up and then you jerk it down, then it's going to be a wave pulse of this shape, not of the inverted shape, correct? So this is going to be the reflected wave, right? This is going to be the reflected wave. Clear? This is the incident wave and this is the reflected wave. Understood? Will ring do SHM? Yes. If you would continuously keep moving this, right, then the ring will do SHM. I repeat what I said. They were asked me, does the ring do simple harmonic motion? Well, not in this diagram, because here I am explaining everything just by using pulse. Do you remember the difference between pulse and train? That is wave pulse and wave train. Everyone, do you remember the difference between wave pulse and wave train, right? So if there is a wave pulse, then this will only move up once, down once, and then that's it, right? Then the wave will come back. But suppose instead of a pulse, let's say from here you start continuous motion of source, so that will generate wave train. Make sense? If you start continuous motion of the source, then that will generate wave train. In that case, after this pulse, there will be like this, there will be like this, there will be like, all these are going to come to the string, to the ring. I hope you get what I am saying. Gradually, one after the other, all of this will come here. So here also it will get reflected and it will be traveling back in this direction. Understood? Okay or not okay? So then the ring will do SH. Okay, because you are giving a wave train, then all particles on the string will do SHM. Ring also, right? Okay, so this is clear what we have drawn. How is it different from fixed case? How is it different from fixed case? How is it different from fixed case? What was happening? What was happening when the wave got reflected from a fixed end instead of loose? What was happening at that time? Can you tell me? Can you put it in words, everyone? Come on. Everyone, come on. Yes, in case of fixed end, the reflection would be like this. That is, it would get inverted with respect to this. Clear or not clear? Okay, but over here it is not getting inverted. Is it fine, everybody? Is it fine? Right? So that's exactly what I was asking you. So you may just note it down. Come on, everyone. Let's note it down. It's that for reflection from a free endpoint. Again, free means something that can move without any opposing force, not even friction, remember. So this is ideal case. The earlier fixed point case was also ideal. But like I said, they are not that tough to make realistically. For example, you can take a really well polished rod, okay, and you can take a light ring. So in that case, this can move quite freely, okay. And similarly, if you fix a nail to the wall, it becomes fixed. So for reflection from a free endpoint, the reflected wave does not get inverted compared to incident wave. So here there is also no phase change. I hope that makes sense. Just like in the previous case, we had to write phase change of pi. Here we can just write no phase change. Okay? Alright. Fine. I'm erasing everything over here. Let's draw multiple diagrams. Let's draw multiple diagrams like we have done earlier. Okay, let's start. So, first case, let me draw a little bit of space here. So first case is where the wave just touches the ring. At that time, where is the imaginary wave? Well, the imaginary wave at that time is here. Okay, and it is waiting to come out. I hope that makes sense. Okay, it's not below this, it's on the same thing, but I'm just drawing it separate. The imaginary reflected wave is just waiting to come out towards the left side. Okay? Right, so here nothing extraordinary will happen. This is displacement of ring or last point, okay, or end point. You could say displacement of ring or end point. Okay, but let's draw this after this wave reaches its amplitude. Okay, so this is diagram 1, diagram 2 now. So, like this. Okay? Right? So, here, this is the wave that has already gone. But like it was in the previous diagrams, this part of the wave will become reflected wave. So, the reflected wave on this string at that time would also be like this. Did you understand? The reflected wave would also be like this. Yes or no? This is reflected wave. Clear or not clear? Upper one incident, lower one reflected. Yes or no? This is where something really strange will start. Y equal. Suppose this was an amplitude. So first wave at amplitude. The second wave is also at this point and it is also at amplitude. Do you realize what I am saying? Okay. So what this means is that even if the wave that you have sent, let's say this wave, okay, incident wave, yi, suppose, was something like 5 mm into sine, let's say kx minus omega t. Suppose it was this kind of phi 0 is 0, let's assume. Then this point here in this situation will not get displaced just by 5 mm. It will in fact be displaced by 10 mm. Do you understand why? Do you understand why? Because there are two waves, one incident and one reflected. Both are acting at that same point, at that same time. Okay? This is in stark contrast. This is completely opposite to what we had. This is completely opposite to what we had for inverted reflected wave. Do you remember things like this in case of inversion? Okay? So that is what makes these two cases different. Right? So here, even if this wave has amplitude 5 mm, but still the ring will not get displaced by 5 mm. Its maximum displacement will be 10 mm. Maximum displacement. Clear? 5 for this wave, 5 for this wave. And then I just draw the last diagram. So last diagram will be where the incident wave has completely gone, right? So you could sort of think that this is the imaginary part of that. Okay, it's all gone. Remember, it has completely reached the string. The ring. And on the other hand, the reflected wave, is now like this. Did you understand the three diagrams? Here I have not drawn 5, I have just drawn 3. Okay, I have just drawn 3. Hopefully you got the idea because it's similar to what we studied earlier. Alright? Well, so this is how reflection occurs from a free end or a loose end. Alright? Okay? Well, I'm going to erase the diagrams, right? If you want, you can write this in. If you want, you can write this in words also. How to write it? The maximum displacement of the free end. Maximum displacement of free end, right, is double of amplitude. Clear? Maximum displacement of free end is double of amplitude. Understood? Okay, then I'm going to erase everything that we have got here, right? Now I will explain the role of damping, okay, in physical situations. Now I will explain the role of damping in physical situations, okay, of waves. Let's see. Right? This is extremely simple to understand, at least qualitatively, if you don't want to go into maths, which we are not going into because it's not in your syllabus. Right? Just simple basic idea which you will easily understand. Do you realize that suppose even if there was a fixed wall here, let's say, and you would give only one wave pulse, let's say you generate one wave pulse by holding this source in your hand, then it's not that this wave pulse can continue going back and forth after reflection. You understand? It's that over here, after reflection, its amplitude would decrease. Make sense or not? Do you realize what I'm saying? Over the time, as it passes through string, it hits the wall, comes back, comes to your hand, hits your hand, goes back and all that. Gradually over time, amplitude will decrease. Yes or no? Right? Amplitude will decrease due to reflection, and it will also decrease due to resistive forces in any material. Remember that. Okay? When there is reflection, of course, at that time also a little bit amplitude is going to decrease, right? In reality, remember, most of the time we will be talking about ideal cases, but in reality, what will happen is that the amplitude will decrease even while traveling because of damping and even due to reflections. So, this is where the idea of resonance comes into the picture. Again, let me make you recall what is resonance. Whenever something can oscillate, some physical system can do oscillations, right? Okay, it has something called natural frequency, and if you would apply external force or driving force of the same frequency, then in this case the amplitude becomes very high. Do you remember that? Do you remember that or not? The amplitude becomes very high. Okay? So, if you don't want amplitude to decrease every time, I repeat, if you don't want amplitude to decrease every time it becomes zero, that is, if you want amplitude to be high, then what you should do is you should oscillate this string. You should oscillate this string or the source in such a way that natural frequency of string is same as the frequency of source. Did you understand? Did you understand this? Natural frequency means F0, right? And source is being pushed by which force? By the driving force, right? You take it in your hand and you move it. So that means this is the driving force. Clear? Okay? Fine. So we will build up on this idea next time, that if you want to keep the amplitude high, then you have to oscillate the source at some particular frequency. Right? You have to oscillate the source at some particular frequency. So how much is that frequency? What does it depend on? And all that is what we are going to cover the next time. Alright? Goodbye.